Well, thanks for the introduction, and thanks for inviting me. I will unfortunately not be able to answer all the questions that Nati has posed, but we will start by looking at some of the simpler cases that we do know how to analyze. So nowadays, when you are doing machine learning, it's very common to run into non-convex optimization problems. Whether you are working on something more traditional, like you are fitting some probabilistic models, like topic models, or you are actually training a neural network, quite often you will just have an objective function that is non-convex, and you need to optimize this non-convex function anyways. So there's a difference between theory and practice for non-convex optimization. In theory, the traditional wisdom is that non-convex optimizations are NP-hard in general. So because they are NP-hard, let's try to avoid doing non-convex optimization, and maybe let's use something like convex relaxation. On the other hand, in practice, or especially in machine learning practice, that's not what happened. People were not so worried about the NP hardness results. And people just try to solve these very complicated non-convex optimization problems using very simple algorithms, like gradient descent or stochastic gradient descent, right? And in fact, these algorithms seem to work very well in practice. They actually converge to good solutions. So why is that? Well, it's not that these algorithms are magical algorithms, right? Gradient descent or stochastic gradient descent are some of the most basic optimization algorithms. So gradient descent is just this very simple algorithm where if you want to optimize this function f of x, you just follow the gradient, and that's your next iteration, and you keep doing this until you somehow converge to a point, right? It's known that gradient descent will converge to a stationary point, even for non-convex functions. Here, by stationary point, we mean that this point has zero gradient. So this is known a long time ago. And more recently, we were able to show that gradient descent or some modification of gradient descent can actually converge to an approximate local minimum. But that's really all gradient descent can do. What gradient descent cannot do is that it cannot escape from a local optimal solution, right? If I start gradient descent from somewhere that's very close to a local optimal solution, there's no way that this local search algorithm is able to jump out of the basin of attraction for this local optimal and somehow actually converge to the global optimal solution, right? So the fact that gradient descent actually optimizes many of the non-convex objectives that we see should tell us something about the shape of these objective functions, and the shape is what I mean by optimization landscape. Just as a baseline, convex functions have very simple optimization landscape. The shape of the objective function or the shape of a convex function is very simple because we know whenever you have a point with zero gradient, then that must be a local minimum, and that actually must also be a global minimum if your function is convex. And because of properties like this, convex functions can be optimized very efficiently using a large variety of algorithms. On the other hand, if you look at non-convex functions, in general, the shape of the objective function can be very complicated. There can be many different local minima that may be much worse compared to the global optimal solution, right? There are also other things like saddle points. And in these cases, gradient descent, we can only hope to find a local minimum. So the question that I will be trying to answer in this talk is, since gradient descent actually optimizes many non-convex functions in practice, what are the special properties for these non-convex functions that actually make them easy to optimize, right? What are special properties that make non-convex optimization easy? And before answering that question, I would like to ask a slightly different question. And these two are actually going to be closely related. So the question that got me thinking about these problems first is actually, why are the objectives always non-convex, right? Whenever I try to solve some machine learning problem and I come up with some objective function, It's almost always the case that whatever objective functions that I can come up with is non-convex. So why is that the case? Can I somehow change my objectives to make it convex? So the answer is not likely, because, so what is one reason that make objective functions non-convex? I would argue that symmetry within the objective function is one reason why your objective function has to be non-convex. So what do I mean by that, right? So as an example, in many machine learning problems, in many, not only machine learning problems, but many problems related to machine learning, this is something that's very typical. So the problem asks for multiple components, but the components have no particular ordering within themselves. So the simplest example of that is perhaps, say, it's a clustering problem. So suppose I am given a lot of data points, and I want to cluster, say, these data points into k different clusters, right? And then the solution to my clustering problem, I can think of them as k centers, such that every point is close to one of these k centers, right? So in this case, my solution is going to be these k centers, but I don't care about their ordering. I don't care about whether this one, I don't care about whether this one is called the first cluster or this one is called the first cluster. As long as I have the same set of centers, the solution is going to be the same. And this kind of symmetry actually happens very often in machine learning. For example, if you are training a neural network, then for any hidden layer, you can always permute the different nodes in your hidden layer. And that will result in different weight matrices, but that will give you a network that computes exactly the same function. So why do you get non-convexity if you have symmetry in your problem? Well, here's a simple example, right? So let's still think about clustering. Suppose this optimal solution A here is an optimal solution for some clustering problem. So x1, x2, and x3 are three vectors for the centers of the clusters. And my objective function is going to be some function f that's on x1, x2, and x3, right? There are, of course, many well-known objectives for clustering, like k-means or k-median. But no matter which objective function you use, let's say this is your optimal solution. Well, given this optimal solution, it's easy for me to come up with an alternative solution that should actually have the same objective function value. So in the second solution, the solution actually didn't change, right? The only thing that I did was to swap the name of x2 and x3. So before x2 was this vector and x3 was here. Now I have just swapped their names. The set of vectors are still the same. And because the set of centers is still the same, this should be an equivalent solution. Whatever objective function you have, it should really assign the same function value to these two solutions, right? But now, since these two solutions are the same, if your objective function is further convex, then we know that the convex combination of these two solutions should better also have a good objective function value, right? But the convex combination of these two solutions is going to look like this, right? It's going to collapse x2 and x3 to a single center. So this certainly doesn't look like an optimal solution for a clustering problem where you have three clusters, because in the end, we actually only have two clusters, right? So clearly, this is a suboptimal solution. But if your objective function were to be convex, then the suboptimal solution should be as good as the two optimal solutions. And that's not going to happen. So that's why whenever your objective function has this kind of symmetry property, it must also be non-convex. Otherwise, these trivial solutions are also going to have good objective function value. So because of this, optimization algorithms somehow need to break the symmetry and converge to one of many equivalent local optimal solutions in this case. So in the case of clustering, of course, you can think that if there are k clusters, there can be k factorial equivalent optimal solutions. And somehow, in your optimization algorithm, you need to decide which permutation of the global optimal solution you are going to converge to. Okay, so that's why symmetry brings non-convexity, and symmetry actually also brings other things into your objective function. So one special structure that only happens in non-convex functions are the saddle points. So if we are optimizing a smooth function, a smooth non-convex function with no constraints, then of course we want to get to the global optimum, and we are worried about having local optimum. But there are additional structures that could happen for non-convex functions, and these are called these are flat regions, which are usually called saddle points in higher dimensions. So I can't have a normal saddle point within one dimension. In 2 dimensions, a saddle point looks like the 0, 0 point at x1 squared minus x2 squared. So it looks like this, and it has a direction, which is the x2 direction in this case, where if you go along the x2 direction, the function value actually decreases. So symmetry not only makes sure that your objective function is non-convex and it has many equivalent local and global optimal solutions, it actually also ensures that your objective function is going to have saddle points. So here's a simple example of that. So this is an objective function that's on a vector x in 2 dimensions. And the objective function is minus x2 norm squared plus x4 norm to the 4. Of course, this is just an arbitrary example that I have chosen, but objective functions of this type were not exactly this one, but something similar to this are actually used in things like independent component analysis. But for now, that's not very important. Let's just look at this function. So here, this is a plot for this function where the darker colors correspond to smaller function value, and the lighter colors on the edge, they correspond to the larger function value. And just from this plot, it's very easy to see that there are 4 local and global minima for this function, and they are in the 1, 1, so plus minus 1 directions. And these 4 optima are symmetric to each other because for this function, it's easy to see if I flip the vector x along either the x-axis or let's say the x1 axis or the x2 axis, then the function value is not going to change. So that's the kind of symmetry that we are looking at for this function. And that's also why we have 4 equivalent local and global optimal solutions. So the way you can get saddle points out of symmetry is just by connecting. It's just by connecting 2 local minima using a path. And in this case, I have connected these 2 local minima using this path. And as you can see, along this path, you can actually find a saddle point, which is along the, say, 0, minus 1 direction. So this doesn't happen for every path that connects these 2 local optimal solutions. For example, if I connect these 2 things via a different path, there may not be any saddle point on this path. So the path that we are going to choose is actually going to be the path that minimizes the maximum value, maximum objective function value on this path. So it's the path whose highest point is as low as possible. So if you choose that kind of a path, it's actually possible to show that the highest point on the path is going to be a saddle point. Or it could also be a local maximum, but in our discussion, it's going to be equivalent to a saddle point. Okay, so that's why symmetry not only introduces many different local optimal solutions, it also introduces saddle points. So in particular, if we want to design algorithms for these optimization problems, the algorithms needs to be able to escape from saddle points. And I would also like to clarify one thing, which was a question that I have gotten many times, but never answered very carefully. So a common question is, if symmetry was the only problem that you are worried about for your objective function, why can't you just add some inequality constraints, right, to break the symmetry? And after you have added the inequality constraints, maybe there's now a unique optimal solution that you are looking for, right? So unfortunately, that doesn't always work very well. And here's an example. So this objective function is really the slightly rotated version of the previous objective function. So I have just rotated it a few degrees. And suppose you don't know how I rotated the function, right? You still want to find the global optimal solutions. Well, one way to think about that is, well, the function is still symmetric. So there must be exactly one optimal solution in each of the 4 quadrants. So if I add the constraint that my solution must be in the fourth quadrant, then I know there is a unique local and global optimal solution within the 4th quadrant. So why can't I just do that, right? Let's try to solve a constrained optimization problem such that I search for a local minimum within the 4th quadrant. But unfortunately, that doesn't work because for this kind of a point here, it will actually want to converge to the optimal solution that's in the 4th quadrant instead of the 1st quadrant, right? So if you look at the gradient at this point, it's actually going to go down. And we cannot follow that gradient because our constraint makes sure that the point must be in the 4th quadrant. So this is actually going to be an additional stationary point. Actually, it's going to be an additional local minimum once you want to add these additional inequality constraints. So that's why in many cases, adding these inequality constraints, they do break the symmetry, but they also make the optimization problem harder because I can no longer make sure this point actually converges to one of the local and global optimal solutions. Oh, question over there?
I see why you can't impose inequality constraints, but is there a reason why you can't sort of look for invariances in the function? So like in the previous example, it obviously doesn't depend on the sign of x, just because if you look at the function. And here, there's probably some way that you could find transformations of x.
Right. So it is indeed possible that if you know completely what's the invariance of your objective function, then in some cases you can actually do something to make sure that you account for all the invariances. And people have done this for low-rank matrix problems that I'm going to talk about next. So the only thing that I'm trying to say here is you can't just simply add inequality constraints to do that. You need to be more careful.
I see, and sometimes that might not be possible.
Right. Yeah. Were there more questions? Okay, so let's continue. So this is the kind of new structure that we are going to look at. And I will call functions that satisfy these kind of new structure locally optimizable functions. So more precisely, for locally optimizable functions, their local minima are all symmetric versions of the global minimum. What is the symmetric group really depends on what is the problem that you are looking at. And there's another technical condition that we need in order for you to be actually able to optimize these functions. So that's to say that the functions do not have any high-order saddle points. So this is something that's usually satisfied. High-order saddle points are saddle points that have 0 gradient and also have a positive semi-definite Hessian. So if you just look at the 1st and 2nd order derivative, you cannot tell whether they are saddle points or local minima. In most cases, like most functions do not have high order saddle points. Once you have these 2 conditions, it's actually possible to prove that a large variety of algorithms, including gradient descent or stochastic gradient descent and many others, will always be able to converge to a local minimum. And by the first property, this local minima is also a global optima. So you can just use local search algorithm for all of these problems. Of course, the first constraint is a very strong assumption. why do we believe that all the local minimum are symmetric versions of global optimal solution, right? But it turns out that although this condition is fairly strong, there are actually many interesting problems that satisfy these properties. So the list goes from some of the more traditional problems like the singular value decomposition or principled component analysis. So these are traditional examples of non-convex optimization problems that do not have any local optimal solutions. And then there are problems related to matrices. There are problems related to tensors. And there are some versions of neural networks that I'm going to talk about later. So in the rest of this talk, I'm going to, so this talk is actually structured very similar to Nati's talk, as in the first part, I'm going to talk about these simpler things that has nothing to do with neural networks. But in the end, I will talk about some attempts that different people have done for optimization landscape for neural networks. So for these simpler functions, I will just give an example of matrix completion. So matrix completion, well, there are experts sitting here, but matrix completion, roughly speaking, the problem is you have a low-rank matrix M that you actually don't know. The only thing you know about this low-rank matrix M is that you observe some random entries of M. Based on these random observations and the fact that this matrix is low-rank, your goal is to recover the remaining entries of this low-rank matrix. A typical application of matrix completion is to recommendation systems. In recommendation systems, usually you think of this matrix as a matrix between users and items. And the particular entries are user i's rating to item j. And the reason we believe or we assume that this matrix is actually low rank is because we think of decomposing this low rank matrix into the product of two smaller matrices. So the first small matrix, every row of the first matrix can be thought of as a R-dimensional feature for the user. Every column of the second matrix can be thought of as an R-dimensional feature for the item. And here the underlying assumption is really user i's rating to item j is really the inner product between the R-dimensional feature of user I and R-dimensional feature of item j. So the benefit of assuming this matrix is low rank is because, well, obviously, from the right-hand side, you can see that there are only 2 times n times r parameters. There's actually even fewer parameters than that. So because of that, you can hope to recover the entire matrix using few observations, using something like n times r times some log factor observations. So how do you solve the matrix completion problem? Well, if you haven't seen this problem before, the most straightforward way to do that is probably to write a non-convex objective and try to optimize that. So how do we do that? It's very simple. So I know that every low-rank matrix M can be written as the product of 2 smaller matrices, U and V, right? So I will do that. So I will have variables x and y for these 2 smaller factors. And my hope is going to be x is going to be equal to u, y is going to be equal to v, and m is going to be equal to uv transpose. Okay, and in most of the works, we assume that the observed entries are chosen uniformly at random, and I will use omega to denote the set of all the entries that we have observed from the matrix M. So the first objective function that you will come up with is perhaps this objective, which is very natural. So you just want to minimize, so what do I want? I want xy transpose to be equal to m, right? So how do I ensure that? Well, I have observed some entries of m, right? So let me make sure at least for the entries that I observe, xy transpose is equal to m. And I can do that by minimizing this squared loss function. Which is for all the observed entries, I look at the square difference between mij and xy transpose at ij. And obviously, if your m is actually low rank, then the optimal solution of this is going to be 0, and it's obtained if x is equal to u and y is equal to v, for example. Later in the talk, we will denote this as M minus XY transpose, the omega norm squared. So this is not really a norm, but it behaves really similar to a norm. And the reason I want to use this notation is because, for example, if you observe all the entries of the matrix M, then this objective function is really minimizing the Frobenius norm squared of the difference between M and XY transpose. Okay, so that's our non-convex objective. So as I said, in many cases, the reason this function is not convex is because that there are symmetry within the solutions. So what are symmetry, for example, for this objective function? Well, remember, we hope that x is equal to u and y is equal to v. This is not going to be true in general because there are these equivalent solutions. So by rule of matrix product, we know u times v transpose is going to be equal to u times r transpose times v transpose if R is an orthonormal matrix, if R transpose is identity. So because of this equivalence, if I think of u times r as my new u, say u prime, and v times r as my v prime, then u prime v prime is going to be an equivalent solution. And this is the kind of symmetry that we have in this objective function. And because of this symmetry, the objective function is non-convex, and there are also many saddle points. One of them is going to be x is equal to y is equal to 0. But there are actually more of them. Okay, so what can we say for this objective function? What we can show is that when the number of observations is at least n times r to the 6, remember n is the size of the matrix and r is the rank. All the local minima of this objective function, I have a star here because we need to add some regularizers, are global minimum in the sense that they all satisfy XY transpose is exactly equal to this unknown matrix M. So as a corollary, because all the local minima are good, simple stochastic gradient descent can solve matrix completion from an arbitrary starting point. So you don't need to worry about what optimization algorithm you are using. You can just run a local search algorithm and you will always be able to solve the problem. There are, of course, a lot of other works. So we first did this for a symmetric case, but then later we generalized this to asymmetric case. There are a lot of prior work on matrix completion, which I will not be able to go over. But roughly, they are in two categories. So the first category of work actually solves matrix completion problems using convex relaxation. So these works actually have very tight dependencies on the rank. So they only need n times r times polylog number of observations, which is much better than ours. So the second set of results analyze non-convex optimization algorithms, but they actually require you to use a carefully chosen starting point. And they also have better dependency on rank, I would say. So the second type of results usually have dependency n times r squared. So of course, improving n times r to the 6 is an open problem. Okay, so how can we hope to prove some result like this, that all local optima are globally optimal? Well, the tools that we use are going to be the optimality conditions. So we know that if x is a local minimum of f of x, then the gradient needs to be equal to 0, and the Hessian needs to be positive semi-definite. So this is called the second order necessary condition for a local optimum. And it's very easy to interpret these two conditions because if the gradient is not equal to 0, I can just follow the negative gradient direction and my function value is going to decrease. If my gradient is equal to 0 but my Hessian is not PSD, then I can follow the negative eigendirection of the Hessian and the function value is going to decrease. So the plan that we are going to have is just to go from these two necessary conditions for local optimum, but actually use these to show that x must be a global optimal solution. X must satisfy whatever we want for the global optimal solution. But many of the times we actually do this backwards. So instead of proving this statement, we look at the contrapositive. So we start by looking at a point that's not the global optimal solution. So then what we want to show is actually one of these two necessary conditions is violated, right? And more specifically, we want to show that there exists a direction, delta, that either correlates with the gradient or correlates with the negative eigendirection. So we will call this delta a direction of improvement. And the direction of improvement in this case is really anything that has a correlation with this gradient direction. And the direction of improvement in this case is really anything that has a negative that is negative when you look at the quadratic form of the Hessian. So if we can find a direction of improvement for every point that's not a global minimum, we also have proved that every local optimal must be globally optimal. Because for anything that's not globally optimal, we know how to locally improve it. OK, so how do we do that? So in order to solve matrix completion, we first will look at a much simpler problem called matrix factorization. So in this case, it's a much simpler problem where every entry of the matrix is actually already observed. So the only thing we want to do is to factorize this matrix M, this low-rank matrix M, as the product of two smaller matrices. To make it even simpler, we will consider the symmetric case where this M is equal to U times U transpose. So it's a symmetric PSD matrix. And our objective function is going to be M minus XX transpose Frobenius norm squared. Here we can use Frobenius norm squared because we observe all the entries of M, right? So we don't need to use the omega norm that I defined earlier. So the goal is to prove that all local minima satisfy XX transpose is equal to M. So there's actually a fairly simple proof for this in the matrix factorization case. You will need to believe me in many of the steps, but roughly the proof goes this way. So if we look at the gradient of this function and set it to 0, it actually implies M times X is equal to X times X transpose times X. And in this case, we actually know if X is a full rank matrix, if the span of X is, here by span of X, I mean the span of the columns of X. So if the span of columns of X is equal to the span of columns of M, then it's actually possible to show that M is equal to XX transpose, just based on this gradient condition. So the only problem is the span of X may not really be equal to the span of M. For example, if X is equal to 0, then obviously this gradient is also equal to 0. M times 0 is equal to 0, right? But the span is not the same. So we need some way to make sure that the span of X is equal to span of M, and that actually comes from the Hessian condition. So if your Hessian is positive semi-definite, it's possible to show that the span of X must be equal to the span of M. So this was the approach that we used in our first paper, but unfortunately, to generalize this approach to matrix completion is actually quite difficult. We need many more cases in order to work for matrix completion. So let's look at an alternative approach where we try to find direction of improvement. So intuitively, suppose I have a vector X, I have a matrix X, and it is not at the global optimum. So I want to find a direction of improvement for this X. Well, intuitively, I should just go from X to the global optimal solution U, right? But remember, it's not as simple as that because there are many equivalent global optimal solutions, right? U is only one of these many equivalent optimal solutions. So which one should I go to? Well, intuitively, I should go to the one that's as close to me as possible. I shouldn't go to a one that's actually very far from me, right? So that's actually what we do. So we will actually find the closest local minimum, the closest global minimum among all the optimal solutions. So these calculations, the algorithm doesn't need to do. This is only in the proof. So we will define delta to be the distance between X and the closest global optimal solution. So in picture, it looks like this, right? So here X, it looks like that X is very far from U. But on the other hand, once I rotate U and obtain a equivalent optimal solution U times R, we can actually see that X is very close to this alternative global optimal solution. And the difference between these two solutions is what we denote by delta. And delta is going to be the direction of improvement. So the reason we use this delta is because this delta is going to have nice properties that delta transpose norm squared is less or equal to m minus xx transpose norm squared. So what this means is if delta is not 0, then it must also be the case that my x is also not the global minimum, because if my x is the global minimum, then the right-hand side is going to be 0, and the delta is also going to be 0. Okay, so in our later paper, we actually proved this lemma that says if delta transpose omega norm squared is smaller than 3 times m minus xx transpose omega norm squared, then delta is a direction of improvement. So why is this useful? Well, remember we have this property about the Frobenius norm squared, right? And the left-hand side and right-hand side are exactly the same factors, except the coefficients are different, right? So now for matrix factorization, omega norm is equal to the Frobenius norm. Then it's immediate to see that the left-hand side is always less or equal to 2 times the right-hand side, which is always strictly smaller than 3 times this arrow, unless the right-hand side is equal to 0, right? So unless right-hand side is equal to 0, we can always find a direction of improvement. But if the right-hand side is equal to 0, then m is equal to xx transpose. So that is actually the global optimal solution. So we actually immediately have a proof for matrix factorization once you believe this lemma. And this proof is easier to generalize to the matrix completion case, because what we need in this proof is actually that the omega norm is going to be close to the Frobenius norm for these 2 matrices. So more precisely, we want the omega norm of these matrices to be within a 1 plus minus epsilon multiplicative factor to its Frobenius norm. And we don't need this for all matrices. That's not going to be possible. But we only need these to be true for matrices of the form delta transpose or m minus xx transpose. Both of these 2 matrices are low rank because delta transpose has rank r. M minus xx transpose has rank at most 2r. So as long as you preserve the norm of all low rank matrices, the same proof essentially works because there's a gap between these constants 2 and 3. So if omega norm and Frobenius norm are equivalent up to 1 plus minus epsilon, then the proof would immediately work for small enough epsilon. So this kind of property is actually called the matrix RIP property. It was known before, and it was applied to, it can actually apply to many other problems that are related to matrices. Okay, so that's the basic idea for the proof for the matrix case. As you can see in this matrix example, actually the symmetry is not only useful for understanding why the objective function is non-convex, is also useful for us to find this direction of improvement. Because in finding the direction of improvement, we look at the difference between the current solution with all the symmetry, with the closest global optimal solution. So in some sense, we break the symmetry according to which global optimal solution you are closest to. So there are many more results. Most of these results for local optimizable functions form like they are either problems about low-rank matrices or they are problems about low-rank tensors. And there are some other problems that might be interesting in this category. For example, there are tensor-Tucker decomposition or linear neural network, which I'm not going to talk about in detail. But more importantly, the big open problem here is actually given a new function that has some kind of symmetry, can we very quickly determine whether this new objective for this new function is locally optimizable or not. And we don't have a common framework for doing that. Okay, so in the remaining time, how much time do I have? Sorry.
Still 20 minutes.
Oh, OK, thanks. So in the remaining time, I'm just going to go over some of the attempts that people have done on optimization landscape for neural networks. Optimization landscape for neural networks is actually much more complicated than all of the cases that we saw before. So it's not the case that all the local optima are generated by these symmetry transformations. The symmetry, of course, still plays a role, but it's not going to be the whole story. Before going into the actual results, I'd like to first give a brief overview on deep neural networks, which I'm just going to do it really fast. So we are only going to consider fully connected neural networks here. And the network is going to have a bunch of weight matrices and nonlinearity. Without specific mentions, we will always assume the nonlinearity is the ReLU function, the max over x and 0. So we are going to optimize a neural network over a bunch of samples x and y. So the hope is to learn a network that's able to map every x to the corresponding y. So the network will look like this. So in every layer, you multiply by the corresponding weight matrix, and you apply this nonlinear function entry-wise to the resulting vector. So the function computed by the neural network we will denote it by the function g. And the objective function is going to be a function on the weight matrices for this neural network, which for simplicity, we are just going to look at the L2 loss, which is the difference between y and the prediction of the neural network. Okay. Of course, in practice, in most cases, other loss functions are used, but many of the things that I will talk about could also be extended to other loss functions. And also to make things simpler, we are going to consider in many cases, we are going to consider teacher-student setting. So that's because in this talk, my goal is to focus on proving something about optimization. But for neural networks, there are always other problems like generalization or representation that Nati has talked about, right? So in order to not confuse with those problems, we're actually going to assume there is actually already a good neural network that we call the teacher network that's actually generating the samples. And we are also going to assume that we have enough samples so that generalization is not going to be a problem in most cases. So the teacher network is going to generate the data. So we think of the xy pairs as coming from x from some unknown distribution d, and y comes from the teacher network applied to this input x. And the student network is really just trying to mimic the behavior of the teacher network. So in these cases, we can say that at least we know there exists a good solution, and our only problem is how do we find that solution, right? So we don't need to worry about whether my hypothesis class contains the right function or not. This is, of course, assuming a lot of the things away, but this is what we are doing in order to try to focus on only the optimization problem. So I'm going to go over some attempts in understanding the optimization landscape of neural networks. This is by no means going to be complete. And in particular, there are things that people are going to talk about in the afternoon that I just did not include. So the first example is going to be on linear networks. So these are neural networks that are just actually a product of a bunch of matrices. There's no nonlinearity. And in some sense, you don't need multiple layers for linear networks because you can just collapse all of these matrices into one. But it's still interesting to first look at what can we do if we don't have nonlinearity. So there's actually a lot of people looking at this. It goes all the way back to '88, but more recently, there are many other results. So essentially, what these results show is that all local minimum are global optimal. I have a star there because all of these works, they have different technical assumptions on what x and y needs to satisfy in order to get this result. And they are not really comparable, and it's also not very clear whether those assumptions are necessary. So with 2 layers, we actually know the optimization landscape is very good. There are no higher order saddle points. with 3 or more layers, the objective function can have higher order saddle points, and that is a problem in optimization. And people also know something about critical points. If product of all layers has rank R, which is the maximum possible rank you can achieve, then it is local and globally optimal or a saddle point. So we know a lot about linear neural networks. The main open problem for linear neural networks is actually, does local search algorithm actually find a global minimum? It doesn't follow immediately from existing results, because for neural networks of layer 3 or more, there are actually high order saddle points that we do not know how to escape from. And then next, I'm going to talk about 2-layer neural networks. So these are simple networks where you have an input, and then the input goes to a hidden layer. And we are going to assume that the rows of this first weight matrix are unit norm. It doesn't matter because we are using the ReLU activation function. The output is going to be a linear function on the hidden units. So there's no nonlinearity for the second layer. We are going to make a lot of strong assumptions here. We are even going to assume that the input data X comes from the standard Gaussian distribution, and Y is generated according to a teacher neural network. The goal here is to recover the true parameters A star and B star of the teacher network. To avoid the lower bound examples that Nati mentioned, here, for this 2-layer networks, there are actually some more technical assumptions on A star and B star. Most importantly, that B star is actually full rank. OK, so for this neural network, the first thing that we actually observe is that if you just do the naive L2 loss, there are actually many bad local optimal solutions. If you run it in practice, you will run into these bad local optimal solutions. You will be stuck there, and you will not be able to get 0 training error. So we empirically observed this in our paper, but later it was formally verified. So there are indeed local optimal solutions in this case. So what can we do then? It's not one of the simpler cases where all local optima are equivalent symmetric versions of global optima. How can we deal with these local optima? Well, one idea is, well, we are not really tied to this particular loss function, right? Our goal is to learn the parameters. Our goal is not to optimize this particular function. So let's try to design a new objective that does not have a bad local minimum. So roughly, it looks like this, right? Suppose I have an objective function that has bad local optima. Maybe I can do something to it so that I will flatten out all the bad local optima, and what's remaining are the ones that I want. This is not really a new idea. Changing the objective function is something that people have done before. And the simplest form of that is just to add a regularizer to your objective function, right? There are other examples which I'm not going to go into. So we can indeed do that. We can construct a new objective function for a 2-layer neural network such that under some assumptions, all local minima are globally optimal. And unfortunately, the objective function is quite complicated, and it really relies fairly heavily on the Gaussian input assumption. When the input is not Gaussian, then our objective function does not work. And that's a huge assumption. Later, we were able to relax these assumptions and extend the result to all symmetric input distribution. Again, I have a star because there are more technical things that we need to assume. And the algorithm is actually not a local search algorithm anymore. OK, so let me go into the third attempt. Maybe this should be the first attempt in terms of time. But so people have also been trying to use some physics models, like spin glass models, to compute properties of local minima for neural networks. The main claim here is that maybe not all the local minima are the same, but they are all approximately good. They are all approximately equal to the global optima. And this picture is basically an experiment that shows that. So this is a picture from this paper where they trained a neural network, I believe a 2-layer neural network on MNIST, and the colors correspond to a different number of hidden units. And here you can see that, and the actual plots are histograms of the objective function values of the random local minima that they were able to find using local search. As you can see, in most cases, the value of the local minima concentrate within a small range. Okay, so the proof idea for these kind of phenomena is they actually use a formula to count the number of local min that satisfy a certain property directly. And this might seem very surprising. How can you use a single formula to count the number of local minima? But there is indeed such a formula. I'm not going to try to parse this formula. This is called the Factorization formula. It is well known that you can use this to compute the number of local minima in any region. But of course, this is a very complicated looking formula, and how can you even hope to evaluate this? Well, in some cases, all of these matrices, say the Hessian of f and the gradient of f, these things, in the good cases, they will be random matrices, and in the good cases, they are very nice random matrices like the Gaussian ensemble. So in those cases, you can hope to evaluate the formula using random matrix theory. In the paper, they were able to do that formally for a spin glass model, which are actually random polynomials over the sphere. The connection to the neural networks is not completely formal, but they believe that the same phenomena is happening. Later, this approach of using the Factorization formula was used to prove formal results for some overcomplete tensors and also for the tensor PCA problem. But in general, in most cases, evaluating this formula is still very difficult. So the final attempt that I'm going to describe is going to be to analyze the dynamics of local search instead of the global optimization landscape. So the idea is instead of analyzing the global optimization landscape, we will try to analyze the paths or the dynamics of local search starting from a random initialization. Okay, so why is this going to be easier than analyzing the global optimization landscape? The main observation that many of these works have is that these, in certain cases, there are, especially for overcomplete neural networks, there are local optimal solutions almost everywhere. So no matter where you start, there is going to be a global optimal solution that's very close to where you start. So you can actually hope that these paths are very short paths. And if the path is short, then you can hope to prove some properties using the property of the random initialization, which is very useful if you want to avoid many degenerate settings. So there's a huge number of results of this type that came out just last year. And I'm pretty sure that you will see more results like this this year. So they are in different categories. So the first category focus on empirical risk or the training error. So what they say is actually, suppose your neural network is very highly over-parameterized, then it can memorize your training data, right? It can achieve 0 training error. So this was first proved for a 2-layer neural network, but then it's generalized to multi-layer neural network by several different groups, and also to recurrent neural networks. When you consider generalization, the problem is actually much harder. So here, the earliest paper actually looks at a very special multi-class classification problem. And a more recent result actually does this for 2 or 3-layer neural networks. It's not a general result for 2 or 3-layer neural networks. The result is, in some sense, kernel-like. By kernel-like, I mean the neural network, under their assumptions, is going to be approximable using low-degree polynomials. And it also requires special activation in order for the algorithm to run in polynomial time. Yeah, but so for all of these cases, the common idea is you can actually analyze this path from a random initialization to the optimal solution, and the optimal solution you converge to is actually going to be super close to your random initialization. Okay, so I'm going to end. I'm going to end by two very concrete open problems on optimization landscape that I'm really curious about. So one is on overcomplete tensors. So suppose I have random unit vectors a1, a2 to an. So these are components of a tensor. And n is larger than the dimension of these vectors, but not too much larger, like less than d squared. So I'm going to maximize an objective that's really a degree 4 polynomial related to these vectors over the unit sphere. So the conjecture here is that all local maxima of this objective function, they are either close to plus minus ai for some ai. And empirically, this is indeed true. If you have this objective function, you start from a random point, then indeed gradient descent will always find you one of the AIs. We've tried this on many examples, and they all seem to work. But we don't know how to prove that. So in an earlier paper, I mentioned that we were able to use Factorization formula to say that whenever your f of x is significantly larger than the expectation of f of x, the expectation is taken over the sphere, then there cannot be any other local maxima in addition to these plus minus AIs. But we don't know what happens when you are below this threshold. So proving that you also cannot have local maxima if you are below this threshold is the open problem. So then there's the open problem on neural networks. So my conjecture is, suppose we have the simple setting where we have a 2-layer neural network where there is a teacher network. So suppose, say, the teacher network has, say, 50 neurons in the hidden layer. Then what we empirically observe is if you allow the student network to have, say, 100 neurons in the hidden layer, then you actually always find a very good solution. You will not get stuck in a bad local optimum. As a comparison, if you make sure that your student network also only have 50 neurons, then you will get stuck in a local optimum. So my conjecture is that if W star, the teacher network, has k neurons, let's say W has poly k and epsilon neurons, I'm willing to make other assumptions like the input distribution is Gaussian, because without these assumptions, the problem is still hard. So in this case, maybe all local minimum, maybe they are not all equivalent to the global optimum, but they all have an objective function of value at most epsilon. So that's a concrete conjecture that I'm hoping to prove. So that's the open problems that I'm going to talk about. Thanks.
So we have time for a few questions.
So this gradient descent, there's no issues of that local search being clear or something. You always get this issue.
Right. So this is about whether gradient descent can always get to a stationary point. So it depends on what you are looking for. So it's not clear whether gradient descent can always converge to an actual stationary point. But the result that we are going to need is just that gradient descent can converge to an approximate stationary point, a point that has gradient norm smaller than epsilon. And that is always possible within a polynomial number of steps. Mm-hmm.
Require something like the weight matrices are all sparse. Are there results for that?
Oh, so in the linear network, if you enforce that the weight matrices are all sparse, I believe we don't know any results for the optimization landscape in that case.
Okay, thanks, Rong. So now